Today we will discuss more on the mechanics part. So, in the last class while we were discussing about this transverse force, we saw that we had this term called inertia, right, this I. Now, this I is not mass inertia, this is actually area moment of inertia. Okay. Now, what do you mean by that? So, I will just little bit explain on the area moment of inertia. So, let us assume that this object or this area is at a distance x comma y from in this rectangular coordinate system. Now, area moment of inertia is defined as, like, what is the moment? Moment is that the how far is the area from the from some axis, and let us say if we are calculating the moment of inertia with respect to the x axis, then from x axis it is at a distance of y, right. So, Ix is defined as area integral of y square. Okay. Now, why I am discussing this? Because you need to understand that the area moment of inertia depends on the direction, right. So, while I am calculating the moment of inertia with respect to this with respect to this axis, like the x axis, then it is y square dA. Whereas, if we calculate the moment of inertia with respect to y axis, then it will be x square, double integration of x square dA. Okay. Now, let us consider the beam geometry we have. If we are considering the force, first of all, for this kind of geometry, the inertia I can be written as bh cube by 12, where b is the width or breadth and h is the height. Okay. And we are not going into the derivation of this expression because this is not part of this course. Okay. So, that you can find out from simple mathematics or mechanics. Now, what I want to discuss here, that if the force is in y direction, then this width is considered as width, okay, and this is the height. But if the force is in z direction, like in the along the z axis, then it is perpendicular to this height, means the force is working perpendicular to the height. So, in that case, moment of inertia will be actually hb cube by 12. Okay. So, this is for Fy, whereas this is for Fz. Okay. So, you need to consider that means many a time for this kind of simple cantilever beams, we directly use that area moment of inertia is equal to bh cube by 12 or wh cube by 12, whatever you call the width. Okay. But there what we need to understand that it is not the width or the breadth is not only the based on the its geometry, it is also which direction the force is working. So, accordingly you have to put the formula, like which is your breadth and which is your height. Now, we will see spring mass system. We have seen that, let us say we have spring and a mass connected to that, then we can simply write that if the displacement is, let us say, x and force acting is F, and spring constant is k, then F is equal to kx. Now, and we are going to model our systems like this spring mass system, so that we can directly use the k value and accordingly we can solve any problem. Now, what is the advantage of using this kind of system? That we will understand that if we have multiple beams which are connected to each other, then we can consider that whether the beams are parallel are in parallel or like in series, and accordingly we can write an equivalent stiffness for the system. So, before we go into all those things, let us first see that what happens if two springs are connected to in a mass in series or in parallel. Okay. So, now see these two springs of having stiffness constant K1 and K2 are connected in parallel to each other to the same mass. Now, if I apply some force F, then it is going to deflect by same amount for both the cases. Let us say that is x. So, K1 and K2 spring both will deflect by x, right, but the force will be different in these two cases, right. So, let us assume that the reaction force here is F1 and reaction force here is F2. So, we can write that F1 plus F2 equals to F, right. Again, for both the cases deflection is x only. Now, F1 is equal to then K1x and F2 is equal to K2x, right. Now, the total force is equal to then K1 plus K2 into x. Okay. Now, if we consider this system as a single spring mass system, then we can model it like that, right. So, this is let us say K equivalent, and then you are applying the same force. So, for this equivalent system, then we can write that this is equals to K equivalent into x. So, K equivalent is equal to K1 plus K2. So, if two springs are in parallel, we can directly get the equivalent spring constant simply by just adding their stiffness constants. Okay. So, this is one important relation, and now let us go to the next case where two springs are connected to one single mass in series. Let us say the mass moved by x because of the force F. Now, this spring will have different deflection and the other spring will have another deflection. So, let us assume that K1 will deflect by x1 and K2 will deflect by x2. The force for both the cases are same because they are in series. So, we can write that F is equal to K1 x1 and F is equal to K2 x2. So, x1 equals to F by K1 and x2 equal to F by K2. Okay. Now, if this system is modeled as an equivalent system where we have only one spring constant, right, and then one single mass, so also will have a force of F, and then this, let us assume this is K equivalent S. Last one, let us assume this is K equivalent P or parallel, and this is S for series. So, then you can write that F is equal to, it will have the same total deflection, right, x, same total deflection x. So, F is equal to K equivalent for series into x. Now what is x? X equal to x1 plus x2, and from there we can write that x equal to f by k equivalent series equals to f by k1 plus f by k2, or 1 by k equivalent series equals to 1 by k1 plus 1 by k2. Okay. So, this is another important relation, and for most of the problems, like complicated problems, what we will try to see that if two beams are connected in series or in parallel, and accordingly we will first find the individual spring constant for those beams, and just can apply the series or parallel spring formula and can calculate the combined stiffness constant. Now we will discuss different constants, and constants means like for a beam structure and applied forces, what kind of constant are applicable for that particular beam, means what motions are allowed and what motions are not allowed. Like for this structure, you can see that for the left hand side there is no motions are allowed, like x direction, y direction, z direction, no motion are allowed, as well as rotations are also not allowed, right. But for this end, it can have all the motions are free, like x, y, z, it can move as well as it can rotate. Whereas for this particular case, only we had movement in the x direction. But for transverse case, you see movement was in, or the deflection was in y direction, whereas because of very small deflection, we have considered that the x direction has not in the x direction it has not moved much, but technically it can move in x or z direction also, or even it can rotate. Now I will see that how different constants work for different kind of geometry. Now let us go through different kind of constants one by one. Now first take the first case, like this simple cantilever beam, where one side of the cantilever, like the left side, is fixed and the other side can move, and in this case, see, this side is totally fixed. So it has reaction forces in x direction, y direction, as well as z direction. Let us say we are not considering the z direction in this plane or in the plane of paper. It can rotate, right. So it has x direction force, y direction force, and also the rotation. But this end is totally free. So there is no reaction forces either on horizontal direction or vertical direction or even rotation. No forces are there. Now if we consider a fixed beam, then what happens in a case of fixed beam? And for fixed beam, both the ends are totally fixed. So this end also it cannot move, and this end also cannot move. So the reaction forces will be in horizontal direction, vertical direction, as well as in the rotational direction. Okay. Now the next case is fixed pin. In fixed pin case, you see, pin means that it can rotate across this pin point. So if it can rotate along this pin point, across this pin point, then there will be no movement at this end. Okay. But this is fixed, so it cannot have a linear deflection. So the horizontal and vertical reaction forces will be there. While the motion is restricted, then only reaction force is present, right. So this end will have horizontal and vertical reaction forces, but the moment will not be there, because it is able to rotate with respect to this pin point. Okay. But at the other end is anyway totally fixed, so it will have all the forces and also moment. Now the next case is fixed sliding. What does it mean? Means it can rotate at this point as well as it can actually move in the x direction. If it can move in x direction, then that means that the motion in x direction is not restricted. So, the reaction force will not be there. Also, it can rotate along this pinpoint. So, the moment also will not be there. So, the only reaction force will happen will be present in this fixed sliding case is vertical direction reaction moment. Then again fixed sliding, where the vertical direction is motion is allowed, but the horizontal or the x direction motion is not allowed, and in that case only the reaction force will be present at x direction. Now, this is very important, the last case, that is fixed guided. Fixed guided means what? That it can slide in y direction and there is no rotation allowed. So, it is like this, that one end it is fixed and the another end can move, but like this, okay, can move but like this. So, there it cannot rotate, but it can move. It cannot rotate, but it can move. You see the motion of this metal scale, that here also it is totally fixed, and this end, my right hand is actually moving. My right hand is actually moving, but this I am not allowing it to rotate. Okay. So, this end will have the moment as reaction force and also the x direction, because x direction also no motion is allowed, only the y direction motions I have allowed, right, and that too without any rotation. So, this is guided. So, this beam is guided only in this direction, vertical direction. So, accordingly only the horizontal reaction force and moment will be present. So, now we will see one example based on the concepts whatever we have discussed. So, here are two beams, okay. There are two beams, and in these two beams the length of the beam is same, but the area of cross section is different. Okay. So, let us assume this L and L is the length and A1 and A2 is the area of cross section. Now, these two beams are connected to this particular mass of M, which is accelerated by some acceleration Ax in three different cases. In the first case, these two beams are connected like this. In the second case also these two beams are connected in the opposite direction, and in the third case these two beams are connected like this, right. Now, M is equal to, let us say, 50 microgram, L is equal to 100 micrometer, A1 is 4 micrometer square, A2 is 25 micrometer square, and the acceleration which is applying on the mass is 9.8 meter per second square, and the Young's modulus constant Y or E, whatever you call it, is 150 gigapascal. We need to calculate the equivalent stiffness constant and also the deflection of the mass. What is delta x for different cases? Let us say case A, case B and case C. Okay. Now, the first thing you see in this problem is, in all the three cases, both the beams are under axial stress. So, under axial stress, then we can directly apply the stiffness constant of an cantilever beam which is under axial stress, and that is what we found out, that is WHE by L, right. And here W into H is the area and E is the Young's modulus. So, now let us say we will just, then the formula for our case will be A into Y by L. K1 means the thinner beam and K2 is the thicker beam. Let us say K1 is equal to A1 Y by L and K2 is equal to A2 Y by L, and if you put the values, then you will get K1 equals to 4 into 10 to the power minus 12 into y is 150 gigapascal. So, that is into 150 into 10 to the power 9, right, and then L1 is 100 micron. So, that is 100 minus 6 equals to 6000 Newton per meter. And similarly, K2 will be how much? K2 will be just here, it will be 25 and it will come as 37,500 Newton per meter. Okay. And also we know the force is also same for all the cases, because the same mass and same acceleration is equal to m into ax and equals to your m is 50 microgram and g is 9.8 meter per second square, 0.49 micronewton. Now, for these three different cases, the beam arrangement is different. The first case, the A case, see that both the beams are connected parallelly, because it is the same deflection which will happen for both the beams, right, because they are in parallel. So, it cannot, both the beams cannot have separate deflection. And for B case also, it is, though it looks like series, but it is actually parallel, because in this case also both the beam is having the same deflection. So, this is very important point. You need to understand that this is not only how it looks like, this is what you need to see, that whether the same force is same or the deflection is same. As we discussed that, see, for the parallel case, while two springs are in parallel, then what happens is same force, like same deflection, but different forces are applied, right, on the two different. Whereas if two springs are in series, then you can see that it is like same force is applied as they are in series, but it is two different deflection, x1 and x2, right. And in this case, in this example, now for the case 1, like case A and case B, in both the cases the deflection is same. So, in this case we can say that the beams are in parallel, right. So, we can write that K equivalent for A or B, for both the case, it is K1 plus K2, and this is equals to 37,500 plus 6,000, 43,500 Newton per meter. Okay. So, now delta or deflection for both the case A comma B or A or B is equals to what is my total force, F divided by total spring constant K equivalent, and that is equals to 0.49 micronewton divided by 43,500 Newton per meter. So, note another thing, that this meter will go at the top or the numerator, right. So, and this should be like that only, because this is the deflection. So, deflection should have a length unit like meter, centimeter, like that, right. So, this is correct, 0.0113, okay, 0.0113 nanometer. Now, for the C case, see this is in series, because it is the same force which is applied, but the deflection is different, right. So, for this case, if the equivalent spring constant is K equivalent C, then we can write that K equivalent C equals to 1 by K1 plus 1 by K2, So K equivalent C equals to K1 K2 divided by K1 plus K2, right? And if you put the K1 and K2 value, then you will get 5172.4 Newton per meter. And then what is the deflection? Deflection is delta xc equals to force is again same divided by K equivalency, right? Force is equal to deflection into stiffness constant. So we already got the equivalent stiffness constant for C case, and then just force by the stiffness. So that will give you how much was the force? Force was something about 0.49 micronewton, which is 0.0948 nanometer. Okay, so we have now found the deflection for all the three cases.